Okay, so air with a density of 1.29 kilograms per cubic meters flows at 2 meters per second, where a duct is 48 centimeters in diameter under a pressure of, that's by the way, 1 bar, I believe. What is the A, velocity, and B, pressure when the pipe narrows to 12 centimeters? So notice that the height doesn't change, so our rho gz terms will be the same. Let's figure out the velocity here. Okay, so that'll be a separate problem. Okay, so A1, V1 is A2, V2. So oftentimes you have to solve a continuity problem here, right? It's 48 centimeters in diameter, so we have pi times 48 centimeters, so 24 centimeters in radius, so 0.24 squared, and then it's going 2 meters per second, right? Is equal to, and then it's narrows to 12 centimeters, so it's going to be pi times 0.06 squared times V2, and we're trying to solve for V2. Okay, so pi times 0.24, I know I don't have to put the pi in there, but it's too late, I've already done it. Okay, times 2 divided by pi divided by 0.06 squared is 32. Wow, it really books along here. The chances that that's laminar and all this stuff is fairly small, but let's just go with it. 32 meters per second. So this is 2 meters per second. This is 32 meters per second, right? Okay, so now let's set up our Bernoulli. Right, so 1/2 rho V1 squared plus rho g z. I'm not used to using z, plus P1 equals 1/2 rho V2 squared plus rho g z2 plus pressure 2. All right, and we're solving for the pressure 2, right? So this is 2. Okay, now I'm going to say that the center of the pipe is the same elevation, so we don't have any contribution from hydrostatic pressure. It's just these terms here. So let's go 1/2 times 1.29 times 2 squared plus, and then that pressure right there is 1 times 10 to the 5th, 1.00 times 10 to the 5th pascals. That's P1, right, is equal to 1/2 1.29 times, and then this velocity is 32, right? That's a 9, not a 4. Squared plus, and then P2, right? Now, if you're paying attention here, right, this term is bigger, which means this pressure is smaller, right? So this P2 is going to be small, right? Pressure 1 is bigger. And people always think that, well, okay, the pipe constricts like that, so there should be more pressure. But think of it in a different way. Well, let's get the answer, and then I'll explain how to think about it, right? Okay, so let's just do this. So I'm going to start on this side. So I'm going to go 0.5 times 1.29 times 2 squared plus 1 E5. Okay. Yeah, okay, that's funny. That's 1,000. That's like 1 4 zeros, 2.58, right? Okay, so this is 1, 2, 3, 4. 2.58 pascals, right? So basically this term here contributed 2.58 pascals, which is almost nothing. All right, so let's go ahead and do this. So this is 0.5 times 1.29 times 32 squared. Well, that's going to be a little bit bigger, right? So this is 660.48 plus P2. This is pascals also. All right, so I'm going to subtract this from this, and I'll get P2. Okay, so take this number, boom, minus this number. And I get that P2 is equal to, it's almost the same. It's 99342.1, which is, of course, less than 1,000,000, right? Is that right? It is. Yeah, there we go. 99, yeah, but it's not that much less, right? But it's a little bit less, right? Okay. Now, why is this pressure less than this pressure? Let's think about it, right? If you're a particle right here, and you're going from here to here, aren't you accelerating? You have to accelerate. You're going from 2 to 32 meters per second, right? Doesn't that mean that there has to be more pressure behind you and less pressure in front of you for you to accelerate? That's the only way that a gas particle can accelerate, is that there's more pressure behind it, less pressure in front of it, right? So there has to be less pressure here. That's the physics of it. It seems counterintuitive a little bit, but not really, because it has to accelerate. It has to be going faster, okay, when it gets there. So there has to be more pressure behind it, less pressure in front. It's weird. It's kind of weird. All right.